Unit 17, Aqueous Equilibria, pages 240 to 249, and this will focus on the common ion effect. So let's look at hydrofluoric acid in equilibrium. Consider the weak acid. Hydrofluoric acid yields hydrogen and fluoride. Equilibrium is a delicate balance between the amounts of reactants and products and other factors such as temperature and pressure. An analogy of the hydrofluoric acid equilibrium is shown in the figure where the concentration of reactants and products are balanced on a seesaw. What I want you to focus on is it's at equilibrium, so there is a balance, but that doesn't mean that you have equal amounts of your reactants and products. So we have this much hydrofluoric acid, and we have a low ionization of hydrofluoric acid, which is why we have little products. So there's a very small Ka value for this equilibrium because it lies with mostly reactants when it is at equilibrium. The rates of product formation and reactant formation are exactly balanced. For weak acids like HF, the concentration of H+ is small because Ka is small. Let's see the effect of adding a common ion. A salt, sodium fluoride, is added. Remember your solubility rules that alkali metal ion compounds are completely soluble and they will completely dissociate into their ions. A salt, sodium fluoride, is added. The salt contains the conjugate base fluoride, which has the fluoride ion in common with hydrofluoric acid's equilibrium. So there's your common ion. And it's involved in the HF equilibrium as well as the sodium fluoride salt dissociation. So how does the sodium fluoride salt affect the equilibrium of hydrofluoric acid? The extra fluoride from sodium fluoride salt disturbs the equilibrium concentrations of the hydrofluoric acid equilibrium. The hydrofluoric acid reaction is no longer at equilibrium because the fluoride concentration is too high. So adding this salt is going to add more fluoride, and it's going to disrupt the balance of this system that was in equilibrium. And so now we have too much over here, which is going to cause the equilibrium to shift to make more reactants. Le Chatelier's principle tells us that the reaction will respond by reacting to move the extra fluoride. The reaction goes towards reactant spontaneously, which means that we'll have a Q greater than K and a delta G that's greater than 0. So the weak acid, reaches equilibrium, and once it's reached equilibrium, you can add a salt that has a common ion with the acid, in this case the anion, undergoes complete dissociation in view 2, adding fluoride to disturb the equilibrium. Le Chatelier's principle says the reaction will reestablish equilibrium by proceeding towards reactants in view number 3. When you look at salts, see the ions that are created when the salt dissociates. From a kinetic perspective, imagine a forward and backward reaction at equilibrium. The forward and backward rates of reaction are equal. Suppose now a salt containing B is added to the mixture, and this increases the concentration of B, which in turn increases the rate of the back reaction. The reaction is no longer at equilibrium and is proceeding to make more A. So here is at equilibrium, you have equal rates of the forward and the reverse. However, if you increase the amount of B, then you're going to increase the rate of the reverse reaction towards A. Example 17.80. Number 1, what is the hydronium concentration for a 0.3 molar hydrofluoric acid solution with a Ka of 6.8 times 10 to the negative 4? So here we'll do number 1. Write my hydrofluoric acid. Also going to write my law of mass action. And we have a Ka value of 6.8 times 10 to the negative 4. Initial concentration, here's my ice table, is 0.3, and then these are 0, minus x, plus x, plus x, 0.3 minus x, x, x. So here is at equilibrium. So we're going to solve for x by setting up our law of mass action equation. We're going to use the approximation rule, and we're going to not include this minus x. So when I solve this, I get x is equal to 0.01428. And remember that when I find x, I have also found the concentration of hydronium or hydrogen. So this is the concentration of hydronium. that we are looking for. Let's do number 2. What is the hydronium concentration in a mixture of 0.3 molar hydrofluoric acid and 0.2 molar sodium fluoride? So first we need to recognize that the 0.2 molar sodium fluoride will dissociate completely and yield me, since this is a 1-to-1 ratio, I'm going to have 0.2 molar fluoride ions. This is what I care about because it is the common ion between sodium fluoride and hydrofluoric acid. So that's going to give me a starting concentration of 0.2 molar fluoride. I'm starting with 0.3 molar hydrofluoric acid, and we have 0 hydrogen ion to start. So here's my ICE table, and those are my initial concentrations. So adding this salt just adds the initial concentration of this ion. We still have minus x plus x plus x, 0.3 minus x, x, 0.2 plus x. So the question is still how much hydronium or hydrogen. So when I solve for x, I will then know how much hydronium there is. So we'll plug this into our law of mass action. Now that I've set up the equation, I'm going to ignore the plus x and ignore the minus x. So when I solve this for x, I get 0.00102 molar hydronium. For number 1, to check the approximation, you should take the value we got for x, 1.4 times 10 to the negative 2, and divide by the 0.3 molar hydrofluoric acid times 100, and you'll see we are within the 5% rule, so the approximation is valid. Now let's review the calculation results. You have hydrofluoric acid alone gave us a hydrogen concentration of 1.4 times 10 to the negative 2. But when we had the hydrofluoric acid and the salt, we got 1.02 times 10 to the negative 3, which is a lesser concentration of hydrogen that was produced than if we didn't have that salt present. So the presence of the salt decreased the amount of hydrogen that was able to be produced at equilibrium for this reaction. Adding F- from the salt, sodium fluoride salt, disturbs the equilibrium and causes the reaction to shift back towards reactants, HF. The concentration of hydrogen is lower when sodium fluoride is present. So example 17.81, what concentration of sodium fluoride must be added to a 0.30 molar solution of hydrofluoric acid to create a hydrogen concentration of 9 times 10 to the negative 4 molar, and this would be at equilibrium. So if I set up my ICE table, and the question is, how much sodium fluoride do we need to add? And remember, sodium fluoride is going to directly relate to how much fluoride ion we have initially in the concentration. So what I'm trying to determine is this initial value of fluoride. We start with 0.30 molar hydrofluoric acid and 0 molar of H+, and I'm just going to put an F- there because that's what we don't know, is how much of that did we start with. We have minus x plus x plus x, 0.3 minus x, x, and then the amount of fluoride plus x here. So again, working towards this information. Now, we've been told, however, that at equilibrium, this concentration of hydrogen is 9.0 times 10 to the negative 4. So we actually know now the value of x. And so we can plug in our equation, 6.8 times 10 to the negative 4 equals, and I'm going to have my hydrogen, which is 9.0 times 10 to the negative 4, times fluoride plus 9.0 times 10 to the negative 4, divided by 0.30 minus 9.0 times 10 to the negative 4. We can do an approximation where we do not include this term here, and so when I solve this equation, ignoring this term right here, I get a fluoride concentration of 0.226 molar. And because there is a 1-to-1 ratio between fluoride and sodium fluoride, then we know that we started out with 0.226 molar of sodium fluoride in this system. So the common ion effect is when you have a weak acid and it yields the hydrogen and the conjugate base. And then when you have a salt, and the salt is going to dissociate 100% and it's going to yield its cation and anion, and usually it's the anion that is the common ion to the conjugate base, and you will use that as your initial concentration.